Hello everybody, this is lecture 26 and we are going to talk about absolute maximum and minimum in other words absolute extrema of two variable function. This is continuation of 14.7 where we talked about local extrema or relative extrema. Let's revise what we studied in the last lecture. So we started with definition of local extreme, local maximum, local minimum, and then we moved on to their geometrical and algebraic manipulation or explanation. For a two variable function f of a b, which is actually a functional value at a b, is a local max if this is a maximum value among all the functional values in this region, in this open disk. What do I mean by open disk? You take a point in the domain, you take a point AB and draw open disk around it of any positive radius, right? Similarly, f of AB is local mean if it is the minimum value among all the function values in the open region centered at AB, right? Open disk, sorry, at centered at AB. So geometrically, local maxima look like mountain peaks and local minima looks like a valley low point. So if you take and zoom out one of these part, either local mix or local mean part, and you zoom out and get the figure like this, if you see that the slopes of these two lines are zero, so these two slope of these two lines represent, if you see that these two lines are in the space, these two red lines are horizontal, so their slopes are zero, so their slopes represented. Of course, if you talk about the slope of this red line, this actually is a derivative of the function with respect to x, and this slope of this tangent line represented by the derivative of f with respect to y, so they're both zero. So this is exactly what first derivative theorem said. This is first derivative theorem, not first derivative test. So local extrema at AB, if you have a local extrema, this implies that both of the derivative at that point will be zero. So this does not tell us anything, because in the real case scenario, we want to calculate those points for where local extrema occur. And this says that if you know that there is a local extrema at AB, then their derivatives are equal to zero. So this theorem does not really help us. So there is no first derivative the first derivative test in the two variable function case. So but if we can use this and suppose that there is a tangent plane at this point, and if there is no tangent plane, we have already talked about in the previous lecture that then this point would be a saddle point. So if these two slopes are zero and there is a tangent plane, that means that tangent plane would be horizontal. So this can be shown by using this equation. This is a for a function of two variable. This actually is an equation of the tangent plane. If you put these two derivatives equal to zero, then you will get c is equal to f of ab, right? So this is nothing. So this whole surface is nothing but a single functional point at AB. So that means that this tangent plane touches only at f of AB. So that really tells us that if there exists a tangent plane at this point AB, in other words, this point is not a saddle point, that means that tangent plane and plus these two slopes are zero, that tangent plane would be a horizontal tangent plane. So if there is a horizontal tangent plane, then there must be that will be a critical point, and at a critical point there will always be a local extrema. So this is exactly what we have seen here. So this is a critical point where both of the partial derivatives are zero, or one of them or both of them are undefined. So so let's see an example. So if this is an example, we calculated both of partial derivatives, so equate them to zero because they are never undefined. So 0 2 is the critical point. We calculated the function value, which is actually 5, and we algebraically manipulated this function and see that this will never produces a number which is less than 5. So this function always produces a value in the whole domain. This will produce a value which is greater than or equal to 5. So that means that f of 0 to equals to 5 is a local minimum, not local maximum, because this is the minimum possible value which is achieved at this point. So a saddle point, take an example as this is a hyperbolic paraboloid. So if you travel along this blue parabola, this is a very low point, and if you travel along this yellow parabola, this looks like a mountain peak. So that means that uh, this is a saddle point. In other words, if you draw if you take a neighborhood of this point on the surface, there are some points which whose functional value is greater than f of ab, where ab in this case is origin, and there are functional points whose whose functional value is less than this point. So though that kind of points, whenever you have that kind of scenario, that means that वहाँ पे जो आपके पास जो टेंजेंट प्लेन एग्जिस्ट ही नहीं करेगा, क्योंकि यहाँ पे अगर आप टेंजेंट प्लेन ड्रा करेंगे तो वो इस सरफेस को क्रॉस करेगा। तो इसका मतलब है कि इसके 0 0 पॉइंट पे आपका टेंजेंट प्लेन एग्जिस्ट ही नहीं करता, लेकिन स्टिल यहाँ पे आपके दोनों पार्शियल डेरिवेटिव 0 होंगे। सो इसका मतलब है कि ये क्रिटिकल पॉइंट होगा। तो इसके अगर ये क्रिटिकल पॉइंट होगा तो इसका मतलब है कि एक क्रिटिकल पॉइंट या तो आपके पास लोकल एक्सट्रीमा दे सकता है या सैडल पॉइंट दे सकता है। सो इन बोथ ऑफ दीज केसेस 0 0 ओरिजिन इज आवर सैडल पॉइंट। सो दिस इज एग्जैक्टली व्हाट आई हैव told in this definition. A critical point AB is called a saddle point if every open disk centered at AB, there are points whose functional value is greater than f of AB, and there are points whose functional value is less than f of AB, right? So this is neither local maximum or nor local minimum. So this is a saddle point. So this is a geometric interpretation. For algebraic interpretation, you can see that you calculate the critical point. 0 0 is the critical point, but if you take the positive x-axis where y is 0, your function reduces to minus x square, since x is always positive. So this always will be a negative point. And for positive y-axis, this f of x is 0, so this function will be reduced to y square. This will always produce greater than 0. So that means that if you draw an open disk around 0 0, you will always get some points at which function has negative values and some points at which function has positive values. That means that this 0 0 is not is neither local maximum nor local minimum. So 0 0 is a saddle point. So but if you don't have always have to check the local extrema by this algebraic way. There's a beautiful test that tells us that how to check whether a critical point is local max, local min, or saddle point. So what is it? So if you show this determinant is said to be the discriminant of this function. So which is nice. If you open it, so you will get f of fxx fyy minus fxy square. So what does second derivative test tells us? It says that suppose a function and its partial derivatives are continuous. That means first and second partial derivatives are continuous, means they are never undefined. So that means throughout the disk centered at AB, and that f of x AB and f of y v equal to 0. तो कहने का मतलब है कि अगर आपके पास a b पे अगर आपके पास कोई भी पार्शियल डेरिवेटिव अनडिफाइंड हो जाता है तो ये टेस्ट अगेन फेल हो जाएगा। क्यों? क्योंकि यहाँ पे उसने कहा हुआ है कि f of x y and its second and first and second partial derivatives are continuous, right? तो और दूसरा उसने ये कहा हुआ है कि आपके पास दोनों पार्शियल डेरिवेटिव्स जो हैं वो 0 हों। तो अगर ये अनडिफाइंड हो तो आपका सेकंड डेरिवेटिव टेस्ट फेल हो जाएगा। तो लोकल मैक्स होगा ए बी पॉइंट, आपके पास डोमेन का पॉइंट लोकल मैक्स होगा इफ एफ एक्स इज लेस देन 0 एंड डिस्क्रिमिनेंट इज पॉजिटिव। इफ डिस्क्रिमिनेंट इज पॉजिटिव बट एफ एक्स एक्स इज ग्रेटर देन 0, दैट इज लाइक लोकल मीन। सैडल पॉइंट इज व्हेन your discriminant is less than 0, and if your discriminant is 0, that then test is inconclusive. So we've seen this in this example. So find local extreme values of this function. You calculate both of the partial derivatives, equate them to 0 because they are never undefined. So from here you get y is equal to x. You put it in back in f of y, you get a quadratic equation in x. So if this is reduced into this two factors. So from here we get two roots. X is either 0 or x equal to 2. If x is 0, you put here, you will get y 0. If x is 2, you will get y2. So 0 0 and 2 2 are our critical points. We are going to apply second derivative test to check whether these what are the natures of these two critical points. So fxx is minus 6, which is always negative. Fy is 6 minus 12y. Fxy is 6. You can calculate these two from these two derivatives. So discriminant is fxx is f of y minus fxy square. Calculate it and get this. This is your discriminant. So you calculate, so this discriminant at 0 0, you'll get minus 72. So it's less than 0. Whenever the discriminant is less than 0, that point would be a saddle point. So 0 0 is a saddle point, right? So 2 2 is our, if you calculate at 2 2, you'll get 72, which is positive, but your x-axis is negative, so 2 2 will be a local max by the second derivative test. So let's check the limitations of at where second derivative test fails. So sorry. Second derivative test limitations. So we have seen that it does not apply at the boundary points. So if either f of x or f of y or both of them are undefined, second derivative test fails, because it explicitly says that f of x at ab and f of y at ab must be equal to 0. And the third is this third point of this test, that where discriminant is 0. So our second derivative test fails at the boundary points, because it says that it says that throughout a disk centered at AB. So there must be a disk that is contained in the domain about AB. So if you take a boundary point and draw a disk, that will not be contained completely uh, in the domain. So at the boundary points, the second derivative test fails. It also fails where points where these two partial derivatives or either one of them are undefined, or the third one is the discriminant is exactly 0. So now we move on to the next point. So now let's talk about absolute maxima or minima on closed bounded regions. First of all, we should know about what is a closed and bounded region. So if you take this region in the plane, so this is a circle of some radius, uh, but the boundary is not included. This shaded boundary means that boundary is not included. So whenever the boundary of a region is not included, that region would be open. But since it is bounded between you can bound this region in a disk of any positive radius. So this is a bounded region. So this is a closed region but unbounded. So why? Because this black boundary is included, the boundary is included, the interior is included, but you can never pack this region in a closed disk of finite radius, because this goes infinitely. This is parabola, so this goes infinitely in these directions. So this is not a bounded region but closed. Why it is closed? Because the boundary is included, right? So if you take this region, this is a circle, but it is also closed. So interior is included, boundary points are included. So since the boundary is included, this is closed. So you can always pack this region in a closed disk or open disk of a finite radius. That means this is bounded. So we are going to check absolute extrema of closed bounded region. They are closed. That means that boundary is also included. They are bounded. That means you can always pack that region in a closed or finite disk of positive radius, right? So if you need to check the absolute extrema, so these are the three easy three steps to find absolute extrema of so let R be the closed bounded region. So the first step is check the interior points, interior of this closed bounded region. That means that will include local max or mean. These are actually critical points. Second step is boundary points. Let, let it be denoted by B. Since the boundary is included and we are checking or we are investigating the absolute extrema of a function of two variables on a defined by a closed boundary region, so boundary is included, so we have to check boundary as well. So boundary points, and take maximum of and right. So you calculate all the critical points. These are the interior points. These are the points inside this closed region where local extrema can occur, right? Then you check the boundary points, and then take maximum of all these or minimum of all these points. That will be your absolute maximum and absolute minimum, right? So this will be your absolute max, and this will be your absolute min, right? So let me tell you again that second derivative test if fails at the boundary points where the partial derivatives are undefined and where the discriminant is 0. So if you want to use second derivative test to check local extrema, then you cannot check at boundary points, at those points where functions where these two partial derivatives are undefined and where the discriminant is 0, right? So let's move on and solve a question. All right, So let me give you a question about it. So here's an is a question. What does it require? Find the absolute maximum and minimum values of these two variable functions on the triangular region in the first quadrant, bounded by the lines x equal to 0, which is actually your y-axis, y is equal to 0, your x-axis, and this line in the first quadrant. So your bounded region becomes this one. Even if this figure is not given, you can always calculate. You can always draw it, because this is just a region in the plane. This is a closed boundary region in the plane. Since the boundary is included, so that means it is closed. So you can always pack this region in a radius of in a closed disk of radius, some finite radius. That means this is bounded. So this is a closed boundary region. So it requires us to calculate the absolute extrema of this function, right? So first of all, we'll follow this pattern. So first we'll check the interior points. That will include all the critical points. So then we'll check at the boundary, and then take maximum and minimum functional value to be the absolute maximum and absolute minimum of these two functions. So let's start with interior points. So first of all, interior points. So for interior points, we need to calculate both partial derivatives, because that would be the points where the first two derivatives are either 0 or undefined. And if you equate it to 0, you will get x equals to 1, and similarly fy is 4 minus 2y, and if you equate it to 0, you will get fy equals to 2. So 1, 2 is the critical point, and this is the only critical point, because there is no other point where these two functions, these two derivatives are undefined. They can never be undefined, because they are polynomials. They are 0 only at this point. So this is the only point at which we need to check, which is included in the interior, because this is the only critical point in the domain. And what is our domain? This is our domain. This is the closed boundary region is our domain, right? So let's calculate the functional values. F of 1, 2, this is equals to, you can easily calculate it, this is equals to 7. So next we go to boundary points. So the boundary, if you see that this is a triangular region, so there are three parts of the boundary. One includes y equals to 0, this line. The other one is x equal to 0, and the third one is y equals to 9 minus x. So you can easily calculate all these points and the intercepts, because they are easily calculatable. So so let's talk about this region OA first. So we are going to talk about the segment OA. So in this at this segment, we can easily see that y is 0, because this is our x-axis, and at x-axis y is always 0. So you can, if you insert this y is equal to 0 in our original function, so you will get f x as it is, and you replace y 0, and you will get the function 2 plus 2x minus x square, right? This is a single variable function, quadratic function, and it is single variable, and you can easily calculate the boundary on this. What is the boundary of this region, this line segment? Of course, this is the boundary is x from 0 to 9. So now this becomes a single variable question. You need to calculate the extrema of a single variable function. So this is a single variable function, x 2 plus 2x minus x squared is a quadratic equation, and this is the boundary, right? So first of all, let's check up boundary points, because this is a single variable function, and we need to check the boundary points as well. So if x is equal to 0, y is always our 0, because in this whole in all on this segment OA, y will always be equal to 0 because we are checking this line segment, and this line segment lies on the x-axis. So x equal to 0. So that means that f of x is 0, y is of course our 0 because we are in this case. So this is equal to 2. Then we check the other boundary point, which is actually equal to 9. So x is 9, y is 0. So this equals to 2 plus 18 minus 81 equals to minus 61, right? So we have calculated, we have investigated the boundary points. Now we have to check the interior of a single variable function. So how do we check it? You just calculate the derivative and calculate the critical points. So this becomes 2 minus 2x. This can never be undefined. So if you equate it to 0, you will get x equals to 1, right? So x equal to 1. So your x equal to 1, y is 0 because we are in this case. So y is 0. So f of 1 0 gives us the value 3, right? So we have checked this. We have investigated all the boundary points and the inside of this line segment OA. Similarly, now we will talk about line segment. Sorry, not now. We'll talk about, because we are still in the boundary points case. So now let's talk about OB, line segment OB. So on this line segment, if you see this lies on the y-axis, so your x is 0. So now on this line, x will always be equal to 0. So this function will be reduces to, our two variable function will be reduces to f0y equals to 2 plus 4y minus y square. And again, what is our boundary? Why? Because this point is 0 9. Similarly, this point is 9 0. So on this line, the boundary is from 0 to 9. So for at this the boundary is also from 0 to 9, right? So we have already checked. So if you let's check about the boundary points. So we have already checked, if y is 0, then x is also 0. So we have already seen here that this is our f00, right? So f00 has already been calculated. So let's talk about y9. So if y is 9, then x is 0. So that becomes 0 9. So we have here we have checked 9 0. Now we also have to check f, sorry, 0, x is 0 in this case, and y is 9. So that gives us f09 minus 43. You can easily calculate it. You can just put x equal to 0 and y is equal to 9 in this our original function, and you will get this minus 43. So now we have to check the interior points. For that we need to calculate this can never be undefined. So if this is 0, then y becomes 2. So now our x is 0. In this case, critical point is 2. So this becomes f02. This is equal to 6. So now we have checked this boundary points on this line, boundary point on this line. So that left us with this oblique line, right? So let's talk about that. So now we are going to talk about the line segment AB, right? So C part, line segment AB. So at this line segment, y equals to 9 minus x, right? So now x remains x and y becomes 9 minus x. So if you consider this becomes 2 plus 2x plus 4 times 9 minus x minus x square minus 9 minus x square, sorry, whole square. This will give us minus 43 plus 16x minus 2x cubed. So this is again our single variable function, and the boundary of course is again from 0 to 9, so we don't have to check because we have already checked f0, 9, 0, 9, 9, 0 and 0, 0. So all we need to check the interior of it. Let me see. So for this function again, our boundary is 9 to 0. If you put 9, you will get y is equal to 0. So you will be here at this point. So if you take y9, you will get x9. So you will get y0, sorry, here. And if you take y0, you will get 9. So you will be here. So अब हम क्या करेंगे, अब हम ये करेंगे कि हम again इसका interior check करेंगे, right? So that would be, you need to check calculate the derivative. So that is 16 minus 4x. If you create it equal to 0, you will get x equal to 4, and that means we need to check your, so if x equal to 4, your y 9 minus 4 becomes 5. So that means now your point is 4, 5, right? So if you check at point 4, 5, that will give you minus 11, right? So now in this case, the only boundary point is 4, 5, because if you include if you see the boundary points, we have already calculated all the boundary points, so we don't need to do that. So we only need to check the interior of the single variable function. So that would give us only this critical point. At this critical point, the function value is minus 11. So we have done all the calculations. So now just we have completed the first two steps. We have checked the boundary points, we check the interior points of the two variable function, and then we take the maximum and minimum of these two value functions, right? So if you see that the function here is 3, so let's start it with 7, 2, minus 61, 3, 6, minus 43, and minus 11. So functional values, the only candidates are 7, 2, minus 61, 3, 4, minus 43, 6, minus 11. So you take maximum and minimum of these values. So of course the minimum is minus 61 and the maximum is 7, right? So this is f12 was equal to 7, and f90 was equal to minus 61. So at this is the point, this is the critical point at which the function gives absolute minimum, and this is the boundary point at which the function gives the minimum, the absolute minimum. So this is our absolute mean or global mean, and this is our absolute max. So this is how you check the investigate the absolute maximum, absolute extrema of a two variable function. So all you need to check the interior points. That would include the critical points, the points where the first two partial derivatives are equal to zero, or either zero or undefined. So most of the time they will be equal to zero. So you need to calculate them and check the functional value of the function at that point. Then to check the boundary points, and then you take maximum and minimum of all those boundary points. So if you see the questions in the exercise, they will always be equal to these triangular regions, square regions, and all those regions where you can always reduce the function into a single variable function and then calculate it by using chapter 4, which we studied in the MT 101. So this is how you check the absolute extrema of a two variable function. So now let's move on to the plot optimization problem for two variable cases. So here's a problem. A delivery company accepts only rectangular boxes, the sum of whose length and girth perimeter of a cross section. That means if this is, suppose this is a rectangular box we are talking about. So if you cross section, if you take a cross section, this will be a cross section. So the perimeter of this cross section, this typical cross section, will be our girth. Sum of its length and girth does not exceed 108 inch. Find the dimension of an acceptable box of largest volume. Largest volume mean you need to maximize the volume, right? So let's solve it. So we need to so if this is our acceptable box, then length is x. So this is our length, and if you take this red to be its girth, then the perimeter of this red section will be, since this y, this length will be equal to this length, this z length will be equal to this length. So to y plus y 2y, z plus z 2z, since it is a rectangle, so the perimeter of rectangle equals to 2 times its length plus 2 times its width, right? So that means we get x, its length, plus 2y plus 2z equals to 108. That is what this says, that sum of whose length and girth perimeter of a cross section, this is our typical cross section, perimeter is 2y plus 2z. So x, sum of length and girth does not exceed 108. That means this is our constraint. And next we need to maximize the volume. ठीक है जी. So what would be the volume? So if you take the volume will be equal to, length, width, height, right? So now we can reduce this function to a two variable function. Of course this is a three variable function, so from here we can get at x is equal to 108 minus 2y minus 2z, right? So if you put here, you will get a two variable function that would give you 108 minus 2y minus 2z टाइम yz. आपने जस्ट x की जगह पे ये रिप्लेस कर दिया अपनी कंस्ट्रेंट. ठीक है, ये कंस्ट्रेंट कहाँ से आई? Sum of whose length and girth does not exceed 108, right? So this is our two variable function. So now we need to calculate the of course if you see that critical points. So before talking about the critical points, let's see what this function becomes. This function will become equals to 108 yz minus 2y square z minus 2y g square. Since this is a polynomial in two variables, so this can never be undefined. So that means that all we need to check sorry, first we need to so the domain is and since it is never been it can never be undefined. That means that uh, the domain is the whole plane, right? Whole YZ plane. So our domain is the whole plane, right? So next, let's talk about calculating the derivative with respect to y. That will be equal to 108z minus 4yz minus 2z square. Let's take z common, then this will become 108 minus 4y minus 2z times z equals to 0. Because it's a polynomial, it can never be undefined, so all we need to check whether it will, where it will be 0 at first, at what points it will be 0. So with respect to z, it will become y minus 2y square minus 2y square, sorry, minus 4yz. We can in common y take as a common factor, so its polynomial can never be undefined, so it will be equal to 0. So from here we get two cases, either z equal to 0 or 108 minus 4 minus 2 equal to 0. And similarly here we get either y equals to 0 or 108 minus 2y minus 4z equal to 0. So now we need to combine these two cases. So if let's first assume z is equal to, let's first assume z is equal to 0. So if z is 0 and these two cases combined, we will get, if z is 0 and then if you take y 0, that means our point is 0 0, right? And if you take z 0 and this possibility, that means that we will get 108 minus 2y equals to 0. This would give us y equals to 54. So our y is 54 and z is 0. So this is our another point. And now we will take this option. So if you combine it with y is equal to 0, you will get 108 minus 2z equals to 0. So this would give us z equals to 54. And since z is equal to 0 in this case, so that means this would give us y is 0, sorry, yes, y is 0 and z is 54. Now you take this possibility and this one, you solve simultaneously these two equations, and you will get that y equals to z equals to 18. I'm not going to do it, you can easily do it because this is two variable. There are two equations, two variables, you can eliminate one and solve for the other one, and then plug in the value back in the original equation, and then you can get the other value. So these two value will be equal to 18 18. So from here we will get 18 18. So these are our critical points, right? uh, So what do we do next? Because we need to calculate the maximum value of y and z for which this function gives the maximum value. So we need to calculate the value y and z which will be maximum value y and z for which this function produces the maximum value. So we need to look at the local maximum. So in order to see which of these 4 points, 1 2 3 and 4, which of these 4 points are either local minimum or local maximum. So if you see, if you plug in 0 0, so y 0, Z 0, this will become 0, so volume is 0, so we are not going to talk about, because we are talking about we are maximizing the volume. So this is not our case, right? So this left us with 54 0, 0 54, and 12 12. These are all the possible critical points where some of the points could give us the local maximum, right? So for that we need to apply the second derivative test. So here we are. So I just saved you some of your time, so I solved the question already, and now I'm going to explain it to you. Here were we. So these four are possible critical points. Yes, 0 0, 54 0, 0 54, and 18 18, right? So if you take 0 0, the volume would be 0. If you take 54 0, that means your z is 0. Z 0, z 0, z 0, that means your volume is also 0. Similar case is holds for 0 54. So that means that your volume is 0 at this point, this, and this point. So your only possibility remains is 18 18, right? So if you put 18 and 18, your volume is a non-negative value, is a positive value, right? So now we need to check whether this 18 18 is really a local maximum, because it can never be a absolute maximum if it is not a local maximum. Every absolute maximum is also a local maximum. Similarly, every absolute minimum is also a local minimum, right? So I've just done the calculation for those. So this is your with respect to y first variable, second derivative with respect to second derivative with respect to second variable, and your mixed derivative, mixed second order partial derivative, right? So since this is our function, this is a function, or this is our function is, sorry, our function is x equals to z, for yz. That means your first function, your first independent variable is y, your second independent variable is z. So that means our discriminant will become, here it was if it would have been x and z, so this would have been vxx vyy minus vxy square. Now our function is of variables y and z, so this discriminant becomes vyy minus vyz square. So I just calculated here. So I calculated the discriminant at 18 18, it becomes a positive. Similarly, I calculated the mixed partial derivative at with respect to first variable at 18 18, this gives negative. So that means that they have opposite sign. Discriminant is positive. The second order partial derivative at 18 18 with respect to y is negative. That means 18 18 is our local maximum, right? So that means, so this is our local maximum. So next, that means that our y is 18 inch, our z is 18 inch. So you can easily calculate x from this constraint, right? From this constraint. So from this, sorry, from this constraint, you can calculate the value of, if you are given the value of y and z, you can easily calculate the value of x, right? So that means these are the acceptable dimensions, right? X equal to this value, y is equal to this value, and z is equal to x equal to 36, 18, and 18. So if you put it in the plug in back in the value of volume x, y, z, that will give you 11,664 inch cube. If you convert it into feet cube, you will get to 6.75 feet cube. So this is largest possible volume of a box whose sum of length and girth does not exceed 108 inch. So this is an applied optimization problem. There are similar kind of problems in the exercise. You can easily solve them, and we will see how this online recorded lectures go, and then I will try to solve some problem for you in the exercise as well. So for now, this is all. So let me give you a quick revision. So what we did in this lecture, we talked about absolute maxima and minima on closed boundary region. Closed boundary regions means if it is neither closed or not bounded, that means we cannot calculate the absolute maximum. We can never calculate or investigate the absolute extrema on open regions. So they have to be closed and bounded. So this is an open region plus bounded because you can pack it in the in a radius of in a disk of some positive radius. That means this is bounded, but boundary is not included, so this region is open. Here boundary is included, but so boundary is included, that makes this region closed, but you can never pack because it goes infinitely in this direction, so you can never pack this region in a closed disk of finite radius. That means this is an unbounded region. So what we are talking about here is the closed boundary region. That means boundary is included and you can always pack that region, you can always sandwich that region between pack that region in a closed disk of finite radius. So these are the three easy steps to calculate the absolute extrema. First, you check the interior points, that would include your local maximum and local minimum points. So they are always critical points. So first, in order to perform the step 1, all you need to do, you calculate the critical points and check the function value at that point. Then you check the boundary points and take maximum and minimum of all these points. Then that would be your absolute maximum and minimum. So here's an example. Check you need to calculate the absolute maximum or minimum of this two variable function, and this is the over this closed boundary region. So this is closed, this is a triangular region, this joined by these three line segments OA, OB, and AB. On OA, y is 0 because this is x-axis. On OB, x is 0 because this is y-axis, and this is the line y is equal to 9 minus x. So first we check the interior. Step first, check the interior. How do we do it? Check that calculate the two partial derivatives. They are never undefined, so they can be 0 on 0.12. So 12 is your critical point. You calculate the value of functional value at 7. So since the only requirement is absolute maximum and minimum, if the requirement was calculate the relative or local extrema as well, so then you needed to calculate whether this 1 2 is your local max or local min. Now you don't need to do that because only requirement is absolute extrema, right? So if you are required to calculate the both extrema, local and absolute extrema, that means you need to apply first derivative test on this point as well, right? But you can never apply your second derivative test on boundary points. That is the limitation of the second derivative test. That means that you can never do the same thing here on the boundary points. So that means you can either calculate the local extrema, or you can calculate the absolute extrema over closed boundary region, right? So the second step is check the boundary. So boundary comprises three parts: OA, OB, and AB. So at OA, y is 0, so you plug in y0 here, you get a single variable function and perform all that task what you did in the chapter 4 for single variable function. You get these 3 points: 0 0, if x is equal to 0, y is 0, right? If x equal to 9, y is equal to 0, then these are two our boundary points. For interior, we calculated the first order derivative and just derivative and equate it to 0. You get the x equal to 1. Similar, you did the similar process here for OB, and similar for AB. You get all, you cumulated functional values, all the functional values. So these are the candidates for absolute maximum and absolute minimum. This is a maximum possible, this is a minimum possible. So this is your absolute minimum, and this is your this 7 is your absolute maximum, and they occur at 1 2 in the domain, and this occur at 9 0 in the domain. So this is a boundary point, this is an interior point, right? So next, applied optimization problem, applied maximization problem. A delivery company accepts only rectangular box, the sum of whose length and girth. What do I mean by girth? Girth means you take a cross section and calculate the perimeter. Does not exceed 108. That means if this is your length and this is this red square is your cross section or girth, that means 2y plus 2z is the perimeter. So x plus 2y plus 2z is equal to 108. You can calculate the value of x. You can also calculate the value of z here, but calculating x is easier because then you would need x over 2 in that case, right? So this is the simplest possible case. So you calculate x and plug in you need to maximize the volume. What would be the volume of this rectangular box? X, length, width, height, right? X, y, z. So you plug in x here and get a two variable function. Since it's a polynomial, it can never be undefined. That means your domain is the whole open region, unbounded and open region, right? So what we need to do is we calculate v with respect to y and with respect to first variable and with respect to the partial derivative. They can never be equal to, they can never be undefined because they are polynomials into variables. So but they could be zero. So if they are zero, if this is zero, we have two possibilities: either z is zero or this factor is zero. So similar here, either y is zero or this factor is zero. So if you apply this z is equal to zero on these two cases, you get z0 y0 or z0 and this equation, and from this you get 0 0 and 54 0. And similar, if you consider this and this, you get 0 54, and this equation and this two variable equation, calculate and solve it simultaneously, you would get y is equal to z is equal to 18. So that means our critical points are 0 0 54 0 0 54 and 18 18. But at 0 0 your volume is 0, at 54 0 your volume is 0, because every term in this polynomial contains both x and both y and z. So if one of them is 0, so that means that your volume would be 0. So at 54 0 volume is 0, 0 54 volume is 0. So the only candidate left which gives a positive value, that is 18 18. So now we need to check whether it is a local max or local min, because we need to maximize it, right? So in order to be a maximize to maximize it, we need to make sure whether it is a local maximum. It has to be a local maximum, right? So in order to do that, we apply the easiest possible option, that is our second order derivative with respect. So that would need the discriminant, and which comprises the second order derivative first with respect to first variable minus 4z, with respect to second derivative minus 4y, and this is our mixed derivative, right? So you calculate the discriminant. This would give us this polynomial. Then you calculate this discriminant at 18 18. This is positive, and then you calculate vyy, which is actually second order partial derivative with respect to first variable. That would give us negative value. So that this means that 18 18 is, by second order second derivative test, this 18 18 is a local maximum value. So y is 18, z is 18. So plug it back in our constraint, you will get x is 36. So that means our acceptable dimensions are y is equal to 18 inch, z is equal to 18 inch, and x is equal to 13.6 inch. And the corresponding volume would be, you just multiply all these three, and then you will get the maximum possible volume. So this I think this is all. And I think you will have one question after this all. Can we apply a first derivative test? There is no first derivative test in case of single in case of second order derivative, in case of two variable functions, right? Why? I'll explain you a little bit later. So here is the reason that we cannot apply first derivative test, which is applicable in single variable, but we can never apply it in the second variable, in the two variable case. Here's the reason: because if you see what is the first derivative test in the single variable case. So suppose this is a function. So of course this is a local maximum, this is a local minimum. So that would be our critical point c1 c2. What you do is you divide your domain according to these critical points. So that would if your whole real line is your domain, that would divide your real line into three sub intervals. So here is infinite sorry, here is minus infinity, this is minus infinity to c1, c1 to c2, and c2 to positive infinity. Then you check the sign of second derivative by taking some test values. So this here it will be positive, here it will be negative, and here it will be positive. So that means that the second derivative changes the sign from positive to negative on this critical point. So that would make this critical point a local max, and here it changes from negative to positive. So that would make this critical point a local minimum, right? But in case of two variable functions, the thing what happens, this is what happens. So this whole plane is our domain, right? So if this is the critical point a b, so suppose this is the open disk, right? So there are infinitely many ways to approach this point, right? Infinitely many. So suppose if you approach from this line, this changes sign from positive to positive. This could change from negative to negative. This from this on this point on this line, this could change from negative to positive. So there are infinitely many possibilities. For that reason, you can never apply the first derivative test uh, in this two variable case, because there are infinitely many ways to approach a single point in the domain for a two variable case. So that is all. If there is question, you can always send me an email. I will answer those questions. So if I think that is all for now. Thank you very much.